So in this problem we are going to use the material property relationships to calculate strains. So for this problem what we have is a rectangular bar. It's pulled in uniaxial tension, and to define our coordinate systems we have x defined as positive to the right, y positive upwards. So we're going to say that this bar is subjected to a uniform or a uniaxial tensile stress sigma y, which is equal to 100 megapascals. And we're given that the modulus of elasticity E is 207 gigapascals. Poisson's ratio nu is equal to 0.3. So then we need to find epsilon x, epsilon y, and epsilon z. And the way that we'll do that is using Hooke's law. So if you look in the lecture notes, Hooke's law, the equation that relates material properties, is in 3 dimensions anyway, for triaxial stress, is epsilon x is equal to 1 over E sigma x minus nu times sigma y plus sigma z. Okay, so we know that sigma x is equal to 0 since this is uniaxial stress. We know that sigma z is equal to 0 since this is uniaxial stress in the y direction. So if we plug in, so if we eliminate those, this reduces to epsilon x is 1 over E times negative nu times sigma y. So what we have then is that epsilon x is equal to 1 over 207 gigapascals multiplied by negative 0.3 times 100 megapascals. And we will get that epsilon x, the strain in the x direction is negative 144.9 microstrain. And this answer makes sense, especially when we consider that we're pulling the bar in tension in the y direction. So because of the Poisson effect, we do expect that the dimensions will shrink in the lateral direction in x and z. So it makes sense that epsilon x should be negative. Alright, so now let's find what the strain would be in the y direction. And so again, using generalized Hooke's equation, we have epsilon y is equal to 1 over E sigma y minus nu times sigma x plus sigma z. And here we know that sigma x is 0, we know that sigma z is 0. So this reduces to epsilon y is equal to 1 over E times sigma y. And that's just your simple stress-strain relationship now in 1 dimension. So when we plug in our numbers, we won't rewrite the numbers just to save ourselves a little bit of time. But we plug our numbers into our calculator, and we have epsilon y is going to be equal to 483.1 microstrain. Okay, so this one, it's a positive strain, and it's higher than the strain we calculated in epsilon x. So that just kind of a sanity check, ensure that the number makes sense, and it does. And then finally, let's calculate epsilon z. So epsilon z is equal to 1 over E times sigma z minus nu sigma x plus sigma y. And we'll get that epsilon z, knowing that epsilon x or sigma x is 0 and sigma z is 0, we'll end up with epsilon z being negative 144.9 0.9 microstrain. Okay, and then, so this makes sense, right? Epsilon z is equal to epsilon x, right? That makes sense. This is an isotropic bar, so the Poisson's ratio doesn't vary with direction, and neither does the modulus of elasticity. That doesn't vary with direction. So it makes sense that epsilon x and epsilon z should both contract by the same amount when there's a uniaxial tensile stress in the y direction. Okay, so that's how we use the generalized form of Hooke's law in 3 dimensions.